Welcome to our second lesson of our per unit system. In this lesson, we're going to be doing examples, and then the exercises that you have seen on your combined PDF presentation, I will do them on a separate lesson. So it will be lesson 3, which means that this module will have 3 lessons in total. So the first example in our textbook, which is example 6.1 in this chapter, is looking at a transformer bay where you have got an HV side at 480 and an LV side at 220 volts. Then we're given a leakage impedance of J 0.055 ohms, which they said is what is referred to on our low voltage winding. We start then by looking at our HV side of our transformer, and we calculate the Z given base. And that given base is going to be your voltage squared divided by your apparent power. So your voltage on your HV side is 480, and then you're going to square that and divide by the 24 times 10 to the 3. That gives you 9.6, and that 9.6 is not a per unit value, but it's an ohms value. Then you go and we look at what is going to be our Z per unit new base. So we utilize the formula that says it's going to be our Z per unit given base times your square of your voltage given base over your voltage new base. Now, what I want you to look at here so that you don't get confused, the Z given base we just worked out here was 9.6, it was in ohms. But this formula is talking about a Z per unit given base. So it's not the same values that you're looking at. So the Z per unit given base is actually that J 0.055 you were given, which they had said was referred to the low voltage side. So all you're doing now is you're finding out what is this value on our HV side. So you take the one that they've given you and then you multiply by our given base voltage, which is 480 because you're on the HV side, but then your new base voltage becomes the 220, which is what this was at on the LV side. Then that gives us what our Z per unit new base would then be on our HV side. From this point on, you now have a Z given base, which was 9.6, and you've got a Z new base, which is the 0.262. That you can then be able to utilize and work out what is your Z per unit for this transformer. Then we go to our LV side. Then on our LV side, we utilize the same formula for our Z base. We say is equal to our voltage squared over our apparent power. So voltage on the low voltage side is going to be the 220. Then we divide by the 24 times 10 to the 3, and we get that 2.017 ohms. We already know that the per unit on the LV side is the 0.005. So we then take that directly to go and work out what our per unit is going to be. And that is going to be the Z given base over the Z new base, which is going to be the 0.05, which is a given base. And then I divide by that Z base, which was the 2.017 ohms. And that gives me my Z per unit is also 0.0273. So when you look on your HV side, look into your low voltage side, you can clearly see that as long as it is that same transformer, your impedance across the transformer is the same. Either you are on the high voltage side or you are on the low voltage side, your impedance of your transformer is the same. And this becomes important as we go about doing all the exercises that are going to follow. So that you know, as long as you're given an impedance of a transformer, it doesn't matter if you utilize your HV voltage or you utilize your LV voltage to do any calculations on that, because that impedance is the same on either side of that transformer. So that's what this first exercise was really about. Then we go on to see that that is how you would then be able to draw it. And you can see that on the HV side, you've got your V per unit, which you can just assume is 1 per unit. You've got your impedance, and then again on your LV side, you still have that V per unit, which is going to be 1. You always refer to those voltages as 1, 1 on either side. We go on to our second example. So we start working a little bit now from this point on. So here we're given a figure, and they say that it's a schematic diagram of a radial transmission system, and you must use the nameplate values of the generator as base values and draw our equivalent circuit for the system. So what does it mean when they say use the generator as base values? It means that your S new base is going to be the 60 MVA that you need to utilize, and that also your voltage would be the 11 kV. But you must always remember the voltage is tricky because it changes according to the transformer zone where you are relevant with the transformer. The voltage base will change accordingly. All right, then at the bottom of this diagram, you can see that I've just gone and put in all these figures so that they can be straight in front of us. We start now to refer all our impedances to our common base values. So the first part where we're starting is at the generator. Now you remember the formula is going to be your Z per unit new base is equal to your Z per unit given base, and you multiply by your S new base over S given base and multiply by your square of your voltage given over your voltage new base. Now, because we're utilizing the transformer as our base values that we're going to utilize to do the calculations, it really means that your new base for your S and your given base are the same, which is 60 MVA, and also your voltage is the same, which is the 11 kVA. So even if I didn't have to put in the multiplying by the S and multiplying by the squares of the voltages, but I've just done it so that you see what it would have been if they were not the same. Then we go on to the transformer, and on the transformer we're using exactly the same formula as what we did on the generator, but now our new base and our given base for our parent power is different, but it is the same for the voltage. Why? Because on the voltage we're utilizing the transformer voltages as our voltages for the system. And so therefore it becomes your given base and your new base. So in this one, you're going to have your Z per unit given base, which was 8%. Why am I saying 0.08? Because I'm moving from percentage to your per unit. And you do that by dividing your percentage by 100. And if you're moving from per unit to percentage, you simply multiply by 100. So I then take that, and why is it at 90 degrees? I want to explain this because you are given that value as X. So obviously X means that it's an inductance, and therefore that's why, or reactance, that's why you've got it sitting at 90 degrees. Okay, so if it was Z, it would be a combination of your resistance and your inductance. I then take that 0.08 at 90 degrees and I multiply by my 60, which is my new base. That's the generator value I've been told to utilize. And I divide by my 40, which is the given base that I already had on my transformer. And then my answer will simply be the 0.12 at 90 degrees. So you put the voltages or you don't put them in, they don't matter because they're always going to be the same value. And you can utilize either your HV voltage or your LV voltage. As we had said in the 6.1, that your impedance is going to be the same, either you're on the LV or you're on the HV side of your voltage. Then we go and we have our line. Our line, the formula for doing the line is going to be Z actual, which is the 0 plus J 2.9, and I multiply that by my S given base over my voltage squared given base. So therefore, I am going to have the 2.9 at an angle of 90. I multiply by the 60 MVA. That's why I'm putting in my times 10 to the 6. And then I divide by the 132 times 10 to the 3 squared. And that gives me 9.99 times 10 to the minus 3 at 90 degrees, which is similar to 0.01 at 90 degrees per unit. The last one that I'm left with here is going to be my transformer 2. So I utilize the same formula I'd utilize for my generator and my transformer 1. You can see the only formula different is for your line. So just study your formulas. And therefore, on my last transformer now, which is transformer 2, I have my Z per unit times my SNB over SGB multiplied by the square of my voltage given base over my voltage new base. And then I simply have, because it's 7%, it means it's 0.07 at 90 degrees per unit. And then I multiply by the 60, which was the generator we're asked to utilize, and then I divide by my given base of the transformer, which is 30, and then the voltage is going to be the same, so it becomes a 1 squared, and that gives me an answer of 0.14 at 90 degrees. I can then be able to do the last part that they asked for, which is drawing the equivalent circuit. And you can see in my equivalent circuit that I've put in my voltage that talks to the generator, which I can put as 1 per unit. And then I put in all my impedances in there. You can see from the generator, the transformer, the line, and then the second transformer as well. On the third example, it's a little similar to the second example, but there is a slight difference. I want you to carefully look at my generator, and you can clearly see that from my generator, looking at transformer 1, our voltages are not the same. And I mentioned this slightly when we're doing lesson 1, that at generation, they don't always go according to the voltages that we have standard on our transformers. So this is a typical case. Generator is 13.8 kV, whereas it's going into the transformer side at 11 kV. So you can see that my given base for my generator, which is a 13.8, is not the same as my new base, which is the 11 kV, because remember, your transformer determines what is your new base for voltage that you're going to utilize. So let's go into referring all our impedances to our common base values. And I've just summarized what I've said here, that the first thing is that even your S given base and your S new base are not the same. Your S given base, they had said that you must utilize transformer 1 as your base values. So transformer 1 S base is 40 MVA and our generator is 60. So you can see they're not the same. And then for our voltage, as I've already mentioned, your given base for your generator is 13.8, but your new base is 11 kV, which is the transformer closest to it, the transformer that you feed the generator into. And so therefore, we are then going to say take the 20%, which is 0.2 per unit at 90 degrees, and I multiply by the 40, which is my new base, talking to your transformer 1 that we've been asked to utilize, and then I divide by my given base of 60 MVA, and I multiply that then by my voltages, because my given voltage base is 13.8, and then I divide by 11 and I square those, and that will give me an answer of 0.21 at 90 degrees. Then I go to transformer 1. So transformer 1, because we've been asked to utilize it as our base values for the system, it means that my S given base is the same as my S new base, which is the 40 MVA, and obviously your voltage is going to be the same because your transformer determines the voltage that you are going to utilize as your new base. So therefore, it just means that that 8% I'm given is my actual Z per unit. I don't even have to go and multiply by 40 over 40, multiply by 11 over 11 squared, because it's just as ones and ones that are going to cancel themselves out. Then we go to our line. Remember our line, our formula is Z actual multiplied by our apparent power, new base, or rather, sorry, given base, and then we divide by our voltage squared given base. So our S is going to be that 40 that we've been asked to utilize, and then I divide by the 132 times 10 to the 3 and I square that. Then I multiply that by my 0 plus j 2.9, which is really just 2.9 at an angle of 90 degrees, and I get my answer, which is in per unit at 90 degrees. Then I go to transformer 2, which is the last part of this question, and I go and utilize the formula there. Your voltages are the same for given and the new base, so you don't have to put it in if you don't want to. And I've got that at 7%, so it's 0.07 at 90 degrees, and I multiply by the 40 and I divide by the 30, and then I get my answer as 0.09 at 90 degrees. Then I am able to put in the equivalent circuit for that system. Then we now come to example 6.4. And in this example, you have now got a multiple systems that are going into a bus bar. So you've got 3 generators or 3 generating stations all feeding into one network at the end of the day. So they're asking that we determine the Thevenin equivalent circuit for the network that is shown, and we must take S base as 150 MVA and V base as 132 kV on the transmission lines. And I just want you to note what I've crossed out in the red lines. They mixed up my voltages on the LV and HV side. So I've just corrected by crossing out what they've written, and I've written it the other way around right next to it. So transformer 1 is 11 kV to 132, transformer 2 11 to 132, and transformer 3 is 22 to 132. And that actually talks to that V base equals to 132 in our transmission lines. So you can see that our lines are at 132 kV, and our voltages on the LV side of the transformer are really talking also to the voltages that are sitting on our generators instead of how they had written them out before. So the first thing we do is we refer all these impedances to our common base values. And on generator 1, you can see for that entire circuit, I've gone and worked out what for my generator 1 per unit is going to be. And then I've gone and worked out what my transformer 1 and then my line 1 is going to be. So for my gen 1, I ended with the 0.18 talking to the 18%. I multiplied by the 150 I've been asked to utilize as our base, which now becomes my new base. Then I divide by my given base, which was 100. For my transformer 1, I also take that 0.09, which I've been given as our per unit value, and I multiply that by my 150 I've been asked to utilize in the system, and I divide by the 100 that the transformer had as a given base. And then for my line, it simply becomes the 2.9 at 90 degrees because it's J, and then I multiply by the 150 and I divide by the 132 squared. Then I go to my second generator circuit, and on my second generator circuit, you can see firstly that the MVAs there are 150. So that means that my S given and my S new bases are going to be the same. So in my formulas, I do not even have to put in the S new base and the S given base. That's why you see me crossing it out. I then go and I work out my generator there. And remember now, your generator, your given voltage is 13.8. But your new base is the 11. Where does the 11 come from? Is the transformer voltage. It becomes my new base. So then I get an answer there. And then for my transformer too, because the voltages are the same and S's are the same, I can just take that 9% and make it my per unit new base value. And then for my line, I go and take the 4 at 90 because it's a J4, and I multiply it by my S and I divide by my voltage squared. Then I go to my third circuit, which is your transformer 3, your generator 3 circuit. And over there, I work out again the generator, and you can see here your S's are not the same. So I utilize the formula where I've got the S and B over there, SGB. Why am I not putting in the voltages? You can put in the voltages, they're not going to make a difference because your transformer voltage is the same as your generator voltage at 22 kV. So they will just cancel out and make 1. Then I go to my transformer. My transformer is simply that 10%, and I multiply by the 150 over the 250 that I have been given there. And then I work out for my line 3, which is a J5. That means it's 5 at 90 degrees. And I multiply by my S. I divide by my voltage squared. Once I have got all of those 3 circuits done, I can then be able to draw my Thevenin equivalent circuit that they've asked for. And how do I draw this? I simply show that these are all in parallel, and I show that I've got those generators, which are really should be sitting in 1 per unit for all the generators. And then I then simply put in all my impedances that I've worked out, generator, transformer, as well as your lines, and I connect them on the other side as well. And that would be my system as a whole. Because they say a Thevenin equivalent, you can also then add all those impedances together and make them parallel to one another, and you would end up with an equivalent Thevenin volt impedance of 0.118 at 90 degrees. Okay. Then 6.5 is my second last example, and which is going to be a bit similar, slightly different to 6.6. And also is different from what we've seen before because now we have a load, and this load has been defined in terms of kilowatts with a lagging power factor of 0.8. So what do we need to do? Let's first read what the question is asking of us. So they say we've got a radial system and we must use the nameplate values of our transformer. You can see the transformer is sitting at 1 MVA as base values and calculate the terminal voltage on our generator if the load takes full load current at 0.9 per unit volts. So what does that last sentence mean? It means that number one, our generator, we can't make an assumption that it's also sitting at 11 kV. As we've learned, your generator is not always at the same voltage as what your transformer is at, hence we need to calculate it. The second part that they're telling us is that you've got a 0.9 per unit volts that you are going to utilize as your voltage that you have at your load side. All right, so we simply start by working out what is our current in the system. And how do I work out the current in the system? I utilize the power that they gave me at the load, and I work out the current from there. So my power is going to be equal to the square root of 3 V load I load cos theta, which is going to be the 600 times 10 to the 3, which totals the 600 kilowatts. I make it equal to the square root of 3 and I multiply by 3.3. Why 3.3? Because the load is actually at 3.3. Look at the transformer. From the transformer, you have a line and it goes directly to the load. So that's why it's at 3.3 kV. And I multiply then by my current and I multiply by the 0.8, which is my power factor. I am then able to get my current as 1.31216. Then I need to calculate what my base current is. And my base current is simply my S base divided by my square root of 3 V base. What is my S base? They've asked me to utilize the transformer as my base values. So that means it's 1 MVA. And I divide by my square root of 3 multiplied by my 3.3 times 10 to the 3. Again, where is my V base coming from? At the load side, my voltage is the 3.3 and is fed from the transformer 3.3 side, which becomes my base voltage there. So get my base current, and then I can go work out what my per unit current is going to be. And that per unit current is going to be that load current I got initially, and I divide by this base current that I got now. And so therefore I've got a per unit current of 0.75 in this case. Then I must now utilize what I have been given in order for me to work out the impedances of all my different systems. So I start with the transformer because I can't start with the generator. I don't have any information there. So what I'm looking for. So on my transformer, because I'm utilizing that transformer as my base values, it means that my SGB and my SNB are the same. So therefore that 7% becomes my Z per unit. Then I go to my line, and on my line I work out my Z per line, and it's always my Z actual multiplied by my S over my V squared. And that gives me now the 0.8 plus J2.8. And I like this because unlike all the previous example where we had the impedance being a J only, we now have a mixture. And then I multiply that by my 1 times 10 to the 6 and I divide by my voltage squared. And I would be able to get my Z per unit then that I have on my line. Once I then have this, I can use the formula that says my V per unit generator is going to be equal to all of these other voltages together, because we know the voltage when we're talking about Kirchhoff's voltage law, that it is going to decrease as we go towards the load until it gets to be a 0. So that's why my Vgen then equals to these loads put together. Then I can be able to put everything in. Remember, for your load, they said we must utilize 0.9. So that's what you utilize there. And then I take for my line, I simply take the line impedance that I had, which is a 0.61 at 80.27, and I multiply that by my I per unit. And then for my transformer, I take the 0.07 and I multiply by my per unit current as well. So therefore my generator voltage in per unit is 1.088 at 9,335 degrees. I must then transform this into an actual value that you're going to see at the terminals of the generator. And I do that by saying that that terminal voltage value is going to be my per unit value that I just got, and I multiplied by my base value. So my per unit value was the 1.088, and what is my base value? Where do I get my base value from? I get it from the transformer. And then I can be able to say that my voltage at the terminal is going to be that 11,968 at those degrees. Then our last example that we're doing is got a similar network, but you can see now that I've got 2 transformers instead of 1 transformer, and I don't have anything that guides me on the voltage to utilize on my load. So if there is no guidance, like I had in example 6.5, it means I can use 1 per unit when I do the calculation for my voltage. For your load should be at 1. So I start the same way that I did. I work out my current. From my current, I also work out my base current, which then is going to be able to give me what my per unit value is going to be. Once I have that, I can refer all my impedances to my common base values. And I start there by doing your transformer. Once I've got my transformer referred to my per unit, I can already calculate what my voltage on my transformer is going to be by simply calculating your Z per unit multiplied by my I per unit, and I get that answer there. Then I go to my line, and my line is at 1.86 plus J 12.8 ohms, and I multiply that by my S for the system, which is 120 that they've asked us to use, and I divide by the 66 because 66 is the voltage that is on either side of the transformer where the line is. I get my Z per unit and I utilize it with my I per unit to calculate my V per unit for the line. Then I go to my transformer 2 because I've got two transformers in this case, and I do exactly the same thing. And once I have that, I can then work out what my V per unit on my generator is going to be. And remember what I said. I said that you utilize 1 at 0 if they had not given us anything as a reference for the load. So I add all of those together, my load, my transformer 2, my line, and my transformer 1 voltages, and I am able to get what the terminal voltage is going to be, and in this case it gives me that 14.663. Thank you guys, it was a very long lecture. I apologize for that, but go over it a couple of times once you've downloaded it, and tomorrow I will be able to send you those examples that were attached at the end of our PDF presentation.